Today we're going to discuss how to turn heat into work, or more generally, how to get thermodynamics to do useful things for us. Before we get too far into that, there are a couple new concepts or new variables to address. The first is our work. So far our work, W, as we've defined it, has been work done on the system. That is, this is the amount of energy that is entering our system because we are pushing on the piston and compressing our gas or something like that. And if we are doing negative work on the system, if our system is expanding, that means our system is doing work on us, on the environment, and that is the sort of work that is the sort of useful work that we could get out. We're going to define a new variable, Ws, that is the work done by the system, and this is, on the environment or some object in the environment. And the relationship between these two is very, very simple. Our work done by the system is just minus the work done on the system. So here, this work, if it's positive, we're doing work on the system, we're adding energy. Here, if this work is positive, the system is doing positive work on something else, which means it is losing that much energy. Okay, so to recap, positive W means work entering the system, positive Ws means work leaving the system, because this is being done by the system on something else. And we can use whichever one is convenient. It's just important to keep track of it. If you want to be super explicit, you could always just write W on system or something like that, W by system, and that will always let you keep track of things too. And that's fine with me if that makes more sense to you. The book uses this WS convention, which is convenient. The next thing that I want to talk about is thermal reservoirs. So the idea of this is, if we have a large object at a particular temperature, we can add heat to it or remove heat from it without changing the temperature of that object very much. So, for example, let's say we have I think this is the same one the book uses, we have a piece of rock or metal or something that we heat up really hot, and we throw that in a swimming pool. Well, we know that heat is going to leave the hot object and go into the water of the swimming pool. However, it is not going to change the temperature of the swimming pool a significant amount. The swimming pool is going to stay at 22 degrees C or wherever it started. I guess that's pretty cold for a swimming pool, but you get the idea. So that swimming pool can be used as a thermal reservoir. That is, we can put heat into it or take heat out of it. And as long as we're only doing that on small scales, the temperature of that object is not going to change. So thermal reservoirs are not part of our system, but part of the environment that is big enough that the temperature stays the same, T is constant, as we have heat flowing in and out. So these thermal reservoirs can be hotter than our system or colder than our system. So the hot piece of metal system that we put in the cold swimming pool, the swimming pool is an example of a cold reservoir. We also could imagine a beaker of ice water or something like that as a cold reservoir. For a hot reservoir, the most common example is a flame. So here it's a little different because we're like adding energy to the flame to keep it at that temperature. But if you have an object in the flame, that's not going to change the flame's temperature very much. The heat's flowing into your object, flowing into your system, without bothering the flame all that much in many cases. You could also imagine putting an object inside an oven or putting an object in boiling water or something. And in those cases also, if you have enough water or a big enough oven, your system is not going to be changing the temperature of that reservoir very much. The last of the new concepts is what the book calls an energy transfer diagram. These are also sometimes just called energy diagrams, and I guess they are maybe the simple version of a Sankey diagram. If you want to look up what that is, those are super cool also. So the idea of an energy transfer diagram is we represent our system as a little box. And conventionally, we draw our hot reservoir above the system. And our hot reservoir is at some temperature T, H for hot. So our hot reservoir is at this hot temperature, and down here, maybe we have a cold reservoir also at temperature Tc. So maybe this is some flame, this is some swimming pool of cold water, and our system is interacting with both of these things. So we can now draw transfers of energy as arrows on this diagram. So we can have heat flowing from the hot reservoir to the system. So maybe we put our object in this oven or whatever the hot reservoir is. And this amount of heat that flows from the hot reservoir we can call QH. We can also have, for example, our system then, once we've heated it up, we could put it into the swimming pool and have heat flow from our system into the cold reservoir, and that would be QC, the heat into the cold reservoir. In this process, we also may have work entering or leaving our system. We also, I should say, we can have heat entering the hot reservoir and leaving the cold reservoir under certain circumstances. So these arrows do not have to go in the direction I have drawn them. But maybe we'll say, maybe we have work, maybe work is leaving our system, and then we have a picture that looks like this. So conventionally, we would probably keep the values of QH and QC positive and just change the direction of these arrows if heat was flowing the other way. Yeah. All right. So let's do just a couple examples of energy transfer diagrams. I'll reuse parts of this so I don't have to draw it so many times. So here's our system. So in that example that I gave, we have our object, we heat it up in the oven or whatever, and then we take it and put it in the swimming pool, and then we bring it out and it's, back at swimming pool temperature, ready to go back in the oven again. That represents, so we have heat that goes into our object to heat it up. We have then heat leaving our object in to the cold reservoir, and no work is being done. We're not, our object isn't expanding or anything. It's not doing any work. So this is it. This is it for the diagram. So maybe, this could be, I guess I should write W equals 0. So this could be just the conduction of heat from an object, from a hot reservoir to a cold reservoir. We're not doing any work, so this isn't super useful, but conceptually this should make sense. All right, let's do another example. Let's say that we have our block of metal, and instead of putting it in the oven, we rub it on a surface a bunch of times so that the friction increases the temperature. So here we do have energy entering our object, but it is not coming from a hot reservoir. We're not flowing heat into it because of a temperature difference. We are rubbing this object, doing work on it, and adding energy to it that way. So that is going to look like this. We have work in, and then as that object is sitting on the table, if it's warmer than the table, heat is going to flow into our table cold reservoir, and this is the extent of the energy transfer diagram. This is not, not a particularly interesting one, but at least we can use this to represent processes that we can talk about. Okay, we're going to do one more. Before we do that, I want to say there are obvious constraints on what's going on with these arrows, right? So if I have, well, I guess let's just go back to this last one. If I have something that looks like this, work entering my system and then friction turning that into heat going into the cold reservoir, the first law of thermodynamics puts a constraint on the relationship between W and QC. And that is, if there's nowhere else energy can enter or leave my system, then then it has to be the case that the work entering my object equals the heat leaving my object, if this object ends up at the same temperature it started at. So there are constraints on these diagrams from the first law of thermodynamics. We'll get to some specifics of that later. But more importantly, as we will see, well, equally as important as we will see, there are also constraints from the second law of thermodynamics. So let me draw something like this. Let's say we have heat leaving our cold reservoir and entering our system, some amount of heat QC, and then that heat goes into our hot reservoir QH. So our heat flows from the cold to the hot. This could still be allowed under the first law of thermodynamics as long as QC was equal to QH, right? We flow 100 joules of heat into here and then that same 100 joules of heat into there. But this is an obvious violation of the second law of thermodynamics. As we talked about last time, we can't have heat flowing from cold to hot because that would decrease the entropy, which is not allowed. So yeah, this violates the second law just in the same way, you know, if we start with a mug of coffee with milk in it, we can't have the cold milk separate itself from the hot coffee spontaneously. That's not something that happens. Now, if you were careful and wanted to sort out these milk and coffee molecules, you could at least maybe do that, but even then, that's going to take a lot of work. Okay, last diagram I wanted to draw. We have our hot reservoir and our cold reservoir again in our system. So let's say we have heat leaving our hot reservoir, entering our system, and then exiting as work. I guess WS if I'm being careful. So it turns out this does not look like the last diagram we saw with heat flowing from cold up to here and from here up to hot. However, this is equally in violation of the second law of thermodynamics. So this is also totally not allowed by the second law. And we will be able to actually prove why that is in a little while. The effect of this particular system would be to take energy from the hot reservoir and turn all of that energy into work. And that doing that is forbidden by the second law of thermodynamics.